Welcome everyone to the last lecture. We'll give people just a few minutes to join. And if you want to let our panelists know where you're coming from, it's always cool to see how global this community is. Alrighty, we've got a good number of people here, so we'll get started. Of course, today is all about celebrating our students, more than 7,000 students from around the world who have participated in this 8-month-long experience. We've spent the last 25 weeks now all together at this same time, tuning in from 125 different countries and just really embarking on a journey to learning quantum computing and hopefully a lifetime and a career of discovery. So I'll welcome everyone to our final lecture and an official welcome to the quantum community that you all are now integral parts of. And so just quickly, we have a lot of things teed up for today. So just to give you a sense of what the next 2 hours will look like, per usual, couldn't go without me making a few final announcements, but I'll keep those super brief. Then we have an incredible panel with members of the Qubit by Qubit advisory board, leading faculty and leaders in the quantum space. And Fran and Amir will moderate that. As always, we'll take a real quick break, probably just 5 minutes or so before we have a guest speaker joining us from the IBM Quantum team, the corporate partner who has helped make this program possible and free to students around the world. And then our teaching assistants have prepared a special surprise that we'll share with you. We'll hear from Phil and Akshay a little bit about their advice and just reflections on the past year. And then we'll hear from Kira, the executive director of Qubit by Qubit, to send you out with some closing remarks. And so just actually real quick before we jump to the panel, a few final announcements. So at this point, everyone who passed the course, so again, pass-fail grading system, if you had a 60% or higher and passed, you should have received your certificate. So if you have not yet received that, please fill out the form that I'll drop in the chat as soon as I wrap up here. It should have come from a company called Simple Cert, but it should have come directly to your inbox. If you don't see it there, please do check your spam or promotions before reaching out to us. And if you need any corrections, you should submit the Airtable form that was shared in the email about your certificates. And that form will be due Wednesday at midnight. So after this coming Wednesday, midnight Eastern time, we won't accept any additional corrections. So please do check that you have your certificate and that it's accurate. And just one final piece, if you did not submit the form when we asked how you would like your name to be spelled, you wouldn't have received your certificate either. So if you're passing but didn't get it, that could be why. Also fill out that form and we'll help get you taken care of. And please be patient with us. As you all know, there's thousands of students in the course, so give us about 5 business days to make those corrections and we'll get them back to you. Two final announcements before we jump to the panel. So we've posted the technical assessment answers on Canvas. So if you completed that kind of not graded, but kind of final exam to test your knowledge over the course and want to review the accurate answers, those are posted, and it's a great final exercise to figure out where you did really well and areas where you might want to continue studying. And finally, as we've said before, Canvas and Piazza will both be disabled and made inactive on Friday this week. So if there are materials you'd like to refer back to, please do download those onto your computer. Don't circulate them outside of the course, but download those. And once Piazza is inactive, you will still be able to see the past conversations, but there will be no new posts, no new questions, things like that. And I guess I would just like to say really quickly, you'll hear lots of closing words throughout the course of the next 2 hours, but it has been such an incredible joy to be part of this experience and spend these 2 hours with you every Sunday, to join into the labs each week. And we've been reflecting and just reading the comments that students have shared in some of these end of course surveys, and students have brought us to tears so many times just with your gratitude and curiosity and kindness. And so for all of the people who do this full time, all day, every day, just want to say thank you to the students who've made this really, really special for all of us as a staff and a team, to be part of building something new and interesting. And it's only been all of that because our students have been so special. So it's been an absolute pleasure. And with that, I will turn it over to our advisory board members. We have Clarice, Will Oliver, Scott Aronson, and Spiros, who will fully introduce themselves, but folks who've taken time out of their very busy schedules to talk with you and send you out of the course with some words of wisdom. And with that, Fran and Amir, you want to take it over?
Thanks, Rachel. So I guess I will just kick things off by jumping straight into the panel and, as Rachel said, asking all of our advisory board members to introduce themselves, maybe describe your research and other professional pursuits. So I guess I'll start by asking Will, and then maybe we can go around.
Yeah, thanks, Fran. It's really a pleasure to be here today. My name is Will Oliver, and I'm the director of the Center for Quantum Engineering at MIT. I'm also a faculty member there and a lab fellow at Lincoln Lab, which is a national lab run by MIT. So I'm an MIT person. And I also happen to know Fran and Amir really, really well because I've had the pleasure to work with them and still have the pleasure to work with them. And just want to say great job to both of you. I think what you've done this year is really fantastic, builds on what you did for that summer course. So anyways, great job. And also a great job to all the students. I think that it's really fantastic that 7,000 students worldwide took this course. So my research is in quantum computing, and it's quantum computing with superconducting qubits. And those are qubits that are built from superconducting circuits. And we do research from materials to build them, fabrication that we need to make the circuits. And then we test them in refrigerators called dilution refrigerators, get very, very cold, about 200 times colder than outer space. And then we try to make them into larger systems, and we work on the things that you might consider to be, technical challenges. But the things that we have to do if we're going to realize the promise of quantum computing. So that's basically what my research centers on. And to give a scale, we do a lot of research at the 1 and 2 qubit level, and our largest chip today that we've measured has 16 qubits on it. And Amir is about to publish a paper on a circuit with 9 qubits, which is really fantastic. So that's what we do, and we'll have a chance to tell you more.
All right, thank you, Will. I guess next I'll ask Scott to introduce himself and maybe talk more about his work in theory.
Hi, I'm Scott Aronson. So I am a theoretical computer scientist at University of Texas at Austin, and I have been in this field in quantum computing for I'd say about 23 years, and I've been trying to explain this field to the broader public, to journalists, to the business world, to people in other parts of science for quite a long time, through my blog, through articles in the New York Times and Scientific American and so forth. So I have enormous admiration for what the team here at QxQ has built and has accomplished, and I'm proud to be even just peripherally, involved or on the advisory board. Uh, so I got started in this field actually as a summer student with Lav Grover at Bell Labs in the late 90s. And then I was a student of Umesh Vazirani at Berkeley. And my initial interests were mostly about the limitations of quantum computers, trying to prove what they can't do, at least in the black box model, showing that they need many queries to, for example, to find collisions in many to one functions and things like that. I've worked on what is the power of quantum advice states, the learnability of quantum states, quantum money, a bunch of things like that. Maybe the thing that I've worked on that's had the biggest impact has been the theoretical foundations of quantum supremacy experiments based on sampling problems. We started on that around 2010 as really just a pure computer science, undertaking, a purely theoretical undertaking. But then the experimentalists got all excited about it, and I'm sure many of you know what happened next. They said, maybe we could actually do this. And Google, from 2015 onward, said we want to demonstrate quantum supremacy for a sampling problem with 50 or so qubits. And John Martinez's team really made that a central goal. And then in late 2019, they announced that they had done that. And then just 6 months ago, a group at USTC in China announced that they had also reached quantum supremacy. Done some benchmark that was hard to simulate with a classical computer, and that was using boson sampling, which was really the original proposal along these lines by me and Alex Arkhipov from 2011. And both of these claims continue to be debated. People continue to try to figure out, can they improve their simulations on a classical computer in order to spoof, or simulate what the quantum computer is doing. And it's a very exciting time for the field, though. There's going to be a race back and forth for several years. Of course, I expect that for these sampling tasks, before long, quantum computers will have just decisively pulled ahead. But I wasn't expecting quantum supremacy to be achieved so soon. I'm amazed that if anything that we did was able to play a part in that. But I hope that people don't misinterpret it to mean more than it is, to mean that we already have quantum computers that can solve all of our practical problems faster. I think getting to almost all of the practical applications is going to require actually error corrected, fault tolerant quantum computers. And of course, we don't have that yet. And that is, the next big thing that we all hope to see after the achievement of quantum supremacy.
All right, thank you for that, Scott, as well as talking about supremacy, which hopefully will come up again later in the conversation. And then finally, last but of course not least, Spiros, can you please introduce yourself a bit more?
Of course, yes. Hi, everyone. It's a real pleasure to be here, to have this opportunity to speak also with Will and Scott on the future of quantum computing and some of our own journeys. You may not realize that from Will and Scott just introducing themselves, but they are giants in the field. Scott is also a young giant who every time he puts out a paper, everyone just stops and pays a lot of attention, tries to, base their own research program on what he just put out there. But it's important also to be a voice of reason, and there have been fewer and fewer of them as industry is kind of taking over quantum computing, which is also really great that they are putting money into this and growing the field. My personal background is that of mathematical physics. So I'm the annoying kid who is like, but is this rigorous? Okay, like how did you really prove it? Does it work in all possible universes and all that stuff? But my background also is in what is known as quantum many-body physics. So these are quantum systems with billions, or usually I'm more comfortable with infinite number of quantum bits of information, and trying to understand what emergent properties appear from there and how to keep them stable. And it's been really great. I had the pleasure of working with another giant in the field, Matt Hastings, on the quantum Hall effect and trying to understand how is it that macroscopic quantum phenomena can be not just existing in this universe, but also be stable. What does it mean? Like, what kind of ingredients are required? And then this, inspired some other ideas of the universe itself as a hologram being a quantum error correcting code, which is pretty powerful stuff. And what is really interesting in my mind is that your generation, everyone who is here listening to us, right now, and who had the opportunity to go through this amazing course, it will be your generation who will help us figure out how to truly scale up and reliably quantum phenomena, not just as part of quantum computing, but kinds of stuff that you only see in science fiction. And talking about science fiction, one of my other claims to fame is that I convinced Marvel to introduce the quantum realm through Ant-Man and the Wasp, and a bunch of other stuff like Captain Marvel and whatnot. So I try to convince all my celebrity friends to take this seriously and not do the woo-woo quantum stuff that they are used to. So yeah, that's a bit of my background.
Thanks so much for the introductions, everyone. So actually, I would like to pose this question to the panel, and maybe let's have Spiros answer it first. But what was the journey that brought you to quantum computing? Because quantum computing is at least in the form that we know it, is a relatively emerging field, and I'm very curious to hear about that.
Yeah, that's a great question, and it was a very nonlinear path. At least for me, I was supposed to be a mathematical biologist. Actually, my alma mater is MIT, and over there, I worked with one of the finest in the field, modeling how DNA transforms into from primary structure to tertiary and so on and so forth, protein folding, these kind of things. And when I went to graduate school at UC Davis, I was planning to work with somebody who was also really great in that field. But they were so famous that they were never there. They couldn't even be there to sign what I needed, the coursework I needed to get my graduate degree. So I went to the head of the math department, Bruno Nachtergaele, who is semi-famous also within the field as a mathematical physicist himself. And I told him I had an issue, as an administrative issue, but he's like, no, you'll just work with me. You'll be my student. And he had arranged for the whole thing to happen. He just wanted me to work with him in quantum physics instead of just biology. And that's how in fact, he just told me, he's like, how would you like to work on quantum teleportation? And I had no idea what any of that meant. I didn't take much physics, even at MIT or in high school. But because of Star Trek, I was like, I'm doing it. I don't even know what it is, but I'm in. Right? And then I end up reading the Nielsen and Swan, the quantum information Bible back then that we had, and kind of teaching myself, because there weren't many departments at the time outside of the major schools like MIT and Berkeley and others that had quantum information.
Yeah, that's amazing. Scott, I would like to ask you the same question.
Yeah, so I got into computer science, probably because as an 11-year-old, I wanted to write my own video games. They seem like these universes in miniature, and that if you could just understand those universes, which clearly someone did because they had created them, then you would understand something about our universe. And I quickly realized that writing huge amounts of code is maybe not my forte. I'm okay, but to but I got more and more drawn into the theoretical side of it as I learned more. And I was absolutely flabbergasted to learn about the Church-Turing thesis. To learn that the most babyish programming language that I had started with, MS-DOS, QBasic or whatever, could simulate any other programming language, right? That they were all equivalent in their expressive power, and then to learn about the halting problem, to learn about the P versus NP question, that was just, it was just like having my mind blown over and over again. And I knew this was what I wanted to do. And I was always curious about physics, but I always felt like, physicists were just, saying things that were supposed to boggle me about, how an electron is not in any one place until you look at it, but, that were just confusing, and that I just never understood anything, about them. And so I always, hoped that I could just put whatever the physicists were saying just in a box somewhere else, and just keep it from infecting the things that I really cared about. But I would say that in the mid 90s, I was a teenager, and Shor's algorithm had just been discovered, a year or two prior, and I read a popular article about Shor's algorithm, which was talking about how it could try every possible divisor in parallel, right? Which is a complete misconception, right? That's not how it works. And unfortunately, 25 years later, people continue to write popular articles with that same misconception. But I read this, and my reaction was, well, this sounds like obvious garbage, right? This sounds like some physicists who just do not understand the enormity of what they are up against. That this Church-Turing thesis will not be so easily defeated. And what is this quantum mechanics anyway? Who says it's even true? So I decided, I had to read about it. I had a summer internship doing some software development that had nothing to do with quantum computing, but my boss was nice enough to say, yeah, take a few weeks, read up on quantum computing, and give a report about it. And so there were this was the web itself was not that old, but there were already websites explaining Shor's algorithm, explaining Grover's algorithm, which had just been discovered. And I read about these things, and I was amazed that quantum mechanics was really not that hard to understand once you took the physics out of it, right? Once you said, okay, you have a state, it's a unit vector of complex numbers, and then you just do linear algebra on it. You hit it with unitary matrices. And so, I could possibly understand this, right? And not only that, but this field is very new. It's exciting. There's a lot of stuff that's open. There's a lot of stuff that's confusing. Maybe I could even do something here. And then I found out that Lav Grover worked in the same building as me. I went to talk to him. I had ideas for improving Grover's algorithm that were complete nonsense. They just didn't work at all. But Grover was kind enough to offer me an internship with him the following summer. That's when I met students from Vazirani's group at Berkeley, and I said, "Wow, this Vazirani group, I have to learn whatever it is that they know." And it became my dream in life to become a grad student of Vazirani and study quantum computing there. So yes, that is, I wasn't sure that I would stay in that, but it's been 20 plus years since then, and it's just continued to be interesting.
Yeah, that's a very remarkable story. And Will, now I want to pass the torch to you.
Yeah, well, I don't know. My story is a little weird, I guess. I've always enjoyed physics, and I've always enjoyed music. And so I actually started my education as a sound recording technology engineer at a community college. And then I graduated up to a state university at Fredonia. And this was in the early 90s. And at that time, digital signal processing software was pretty rudimentary, but it was starting to become common that you would apply this to writing music and recording music, and then of course modifying and fixing all the things you did wrong while you took that recording. And so I got interested in digital signal processing and computers from that perspective. And I ended up at the University of Rochester, where I graduated, thinking about music and physics and engineering, but my degree is in electrical engineering. So then I went to MIT and I worked with Todd Mackover in the media lab doing an interactive musical performance called the Brain Opera around 1995. And, so that was very interesting. I enjoyed that a lot. But I ended up taking a few courses in the physics department at that time. And one was with Nihat Berker, and it was on quantum statistics. And I just thought, wow, this is really fantastic. Much like Scott said, two electrons cannot be in the same place at the same time, but two bosons, they prefer to be in the same place at the same time. And so I was really curious about that. And so I went to Stanford for my PhD working with Yoshi Yamamoto. And I feel very fortunate there because I worked on quantum optics with electrons. Usually you do quantum optics with photons, but then you can try to do all those experiments with free electrons. And the quantum statistics is different, so you get different outcomes. Basically, there was almost no practical application for this, but it allowed me to think pretty deeply about quantum statistics and comparatively, how electrons behave versus photons, or fermions versus bosons. And then people were starting to think about anyons, right? And so anyways, I graduated, and I was talking with Terry Orlando at MIT, who had just invented the flux qubit with Hans Moy at Delft. It's one of the superconducting qubits. And at that time, I would say superconducting qubits were kind of like the dog of qubits. So in Ike Chuang's famous book, he had, ion traps, and he had probably, atoms in a cavity, falling through a cavity. And then he had sort of the everything else chapter. And so superconducting qubits were in the everything else chapter. They got maybe 3 or 4 sentences at most. So somehow I thought, yeah, that's what I want to do. So it sounded like a challenge. And so I came to MIT, and in particular Lincoln Lab, because I thought, look, if we're really going to do this someday, you need to be in a place that has the infrastructure that's going to allow you to do more than 1 qubit. So at the time, everybody's thinking about, let's just get 1 qubit to work. It's a laboratory curiosity. Gee whiz, look what it can do in my lab. But I was thinking, yeah, I want to do that. I think that's really fun. But I also want to do it with an ethos towards scalability or extensibility. And so by straddling both Lincoln Lab and MIT campus, we could have the best of both worlds, basically, that, we can have the more fundamental exploratory research at MIT campus, as well as the more prototyping, systematic mentality of Lincoln Lab. And that's really defined my career over the last, I guess, 18 or 19 years.
All right, thanks, Will. Going from music to quantum is quite a big shift, but I think the field is very lucky that you did make that shift and are leading the way for superconducting qubits. So I guess now we've heard quite a bit of how you all got into quantum, but considering that you all are professors at very respected institutions, potentially living the dream lives of many of the students in our class, we'd love to hear what a day in the life is like for you. Probably not right now in COVID times, where maybe a lot of it is virtual in nature, but pre-2020, when you could actually be in lab and interact with students, we'd love to hear what that was like. So maybe I'll start off with Spiros.
Sure. Well, it's interesting for us theorists, whether we are like in a guest bedroom at my place here in Los Angeles, or whether I was in my office at Caltech, it kind of feels the same way, even though mostly just over Zoom, interacting with graduate students and postdocs at this point. But yeah, I mean, I gotta say, I feel like I have the best job in the world. Like, I don't know, sometimes people say that. I mean, I really feel this way. A very kind of unique position at Caltech, where I basically research faculty. I don't have to write grants. I have students whoever I want working on whatever I want, but at the same time I get to do outreach instead of teaching. I really love teaching, but I don't have to. So, I'm like, okay, well, instead I can work with Hollywood or with some of the tech giants like IBM and Google and Microsoft to do some outreach to the public in a different way, I guess, that Scott is doing, which is like through this amazing blog and other articles he's writing. But yeah, I think it's freedom. Like, it's so powerful when you're having fun, when you're exploring things that are kind of like at the cutting edge, and you have the freedom to just go deep, right? Yeah, and I wanted to say as a piece of advice to all your students, that even if you were to just take a moment to just go slow, but like dig deeper and deeper along some particular direction of quantum, whatever it may be, you may wonder that, oh, but I'm missing out on all this other stuff. The nice thing is that as you dig, you realize there is a network of connections that connect all these other things as well, right? And the better the research, often the more we illuminate all these paths, how things are connected. And this is something that I love. Like, I love that I could be studying the foundations, the mathematical foundations of quantum physics, what are known as von Neumann algebras and C-star algebras. And then all of a sudden, like, you're starting to come upon, the very nature of time and what it means to have time as an emergent property of the universe as well. And then the same thing with space. And all of a sudden you're thinking of space and time and physical reality, where for thousands of years we thought of them as just like the backdrop upon which things happen, right? The fields and all that stuff. And you think of it in the language of, that your students have been learning, right? Of quantum information theory and computing, right? And trying to, all of a sudden you're seeing that these things are connected. I mean, it's an amazing thing to look at even modern foundations of mathematics and to realize that there's basically the same as the foundations of computer science. And then once you see that, then you're like, oh, this is pretty amazing. It seems to really spill over to all of physics as well. Can I give emergent structures? And it's pretty fantastic. Like, I wouldn't change it for anything.
That's awesome. Thanks, Spiros. And I guess I will ask Scott, who's similarly a theorist, what his day in the life is like, if potentially a bit different from Spiros's.
Yeah. So, if we're being honest, most of my day is dealing with my kids. I've got a 4-year-old and an 8-year-old. It's answering emails, which could be, anyone from colleagues to high school students to, answering comments on my blog, sitting in faculty meetings, trying to, recruit people to UT Austin, dealing with, I'm writing recommendation letters, helping my students and my postdocs and my undergraduates with all of their projects, talking to journalists, talking, these days to investors, all sorts of people. I look back with so much envy, of my past self, right? Who had, just endless hours to spend, working on research problems. And I very rarely get that these days. This was all true before COVID, but it became even more true after COVID. But when I was a grad student, when I was a postdoc, I would just usually not even at a computer, just with paper and pen. If I'm really trying to do something new, right, and just exploring, just playing around, right. And if I'm sitting at a computer, that's because the exploring is done probably, and it's time to LaTeX up a paper, right. But of course, even once you start writing something, then you realize that things you thought you understood, really you didn't understand, and so then you have to go back to thinking about them more. But I would say that I've done lots of collaborative work, where it's made no difference whether the colleague was right down the hall from me or whether they were in Latvia, let's say, right, and we could just email each other data. In fact, that can work better because then you your day's work is to send an email, and then you wake up in the morning and there's a response, and then there's what to think about for you for the next day, right? So I find it really, really hard to think on the fly, right? So sitting at a blackboard with someone else, so I can explain what I figured out. They can explain what they figured out. But then to figure out something new, I just have to go off on my own, and I have to sit with paper and pencil. But I should say, I think it's been like 17 years since I seriously wrote any code. These days, sometimes we will do simulations, but I have so many students who are so much more qualified than I am to code those things up that I would normally have them do it. I did have a business person, a couple of years ago, who was on the phone saying, well, he wants to come tour my lab at UT Austin, and can he see my dill fridge, my dilution refrigerator? So I had to explain, well, you do realize, we are computational complexity theorists. We have a fridge, it's for leftovers. Okay. We've got, we've got a kitchenette, you can see that, you can see our whiteboards, you can see our laptops. But yeah, that's, it's pretty boring to look at, all the interesting stuff is happening in people's heads.
All right, thank you, Scott.
Sure.
I guess I will pass it on to Will, who I know has expressed similar frustrations to Scott in the sense of envying his days as a student, but maybe it's a bit different having actual dill fridges in your lab. Can you tell us what a day in the life is like?
Yeah, well, it's true. It's great to have these fridges in the lab. And Scott, you can borrow one of mine. I don't mind. We'll send one out. You too, Spiros. Why not? Good. Yeah, they get really cold. So I agree with what Spiros and Scott just said for sure. And our days are filled, of course, it's a job, right? And so there are things we need to do in terms of, responsibility to the department, to the institute, and then also to our field, reviewing papers or going out and giving talks. That's of course enjoyable, but it can be also a task, right? And when you're given your fourth talk in a month, right, and traveling somewhere to do it, then that's time away from family and time away from home. But I'm living the life. I wouldn't have it any other way. I think it's great. And what I can say is that I learned today through a couple things. I learned through my students primarily. I love it to go into the lab and talk with them when they're doing experiments, or they may come into my office and tell me something's not working right. I'm still useful. I can go into a lab when there's a problem, and usually I can identify what's going on wrong. I may not stay in there for the next 2 days to fix it, but I can help them troubleshoot and find out what's not working. And then I think the most important part of a graduate student or undergraduate student's life is that aha moment when they've been working really hard and things haven't been working, and then suddenly it just all clicks. You get this fantastic result. And it might be the blip on the screen you were looking for, or you do some data analysis and the oscillations are happening the way you expect. And I think that's fantastic. And I love it that my students can have those experiences and then share them with me. And like I said, I learn every day really from the students and what they're doing. And I also learn from teaching. And so no matter how many times I've taught a course, somebody will ask me a question when I'm at the whiteboard or the blackboard, and it'll stop me in my tracks because I'll start to answer it in the usual way, but the way they asked the question made me realize, oh shoot, this usual answer I give is not complete. There's something else, and that's what they're getting at. And I could snow them by just saying this again, but then I stop and I say, no, I need to think about this a little more. And then I spend some evening and do some paper and pen and realize, okay, yeah, there's this other aspect that I hadn't quite thought about. And I think this is the right way of the world, that students like you, and when you become, graduate students and then hopefully PhD students, that this is the time when you can basically devote every waking hour of your day to just learning and discovering. And I think that that's and my job and Scott's job and Spiros's job is to make sure we create an environment where you can do that. And that's the right way of the world. And then you will graduate and gradually become those leaders that we are today. And you can then enable, 10, 20, 30, 100 people to do the same. And that's how you pass it on. And so that's the way I like to pass it on. But it's also a little bit selfish because I learned so much in doing this that I'm still having fun. So I guess that's what I would say.
Yeah, thank you, everyone. So next question that I want to ask you, and again, since each of you is an active researcher in the field and very knowledgeable of what's happening, is in your opinion, what are some of the most interesting research work that's happening right now in quantum computing? And Will, let's start with you.
Well, Amir, I think your research is the most important thing happening today. It is very interesting. I think that, well, I think a few things. So one, I think, like Scott said, there's entirely too much, and maybe Spiros too, there's entirely too much hype in the field right now. And that hype is real because there is some reality to this excitement, that there is a promise to quantum computing, absolutely. And it holds a lot of potential, but the time frame over which this potential may be realized, or the steps that we need to take, the important steps to realize it, may get masked in this hype. And so what I try to do in my own group is focus on the real problems, at least as I see them. And that's not every problem, but it's the ones that I think are problems today. So these are related to extensibility. I'm an experimentalist primarily. And so the question is, how can I make the best 1 qubit gate and 2 qubit gates? And then how can I study those effects in, say, 10 to 20 qubit systems, right? You can imagine that if you just make one perfect qubit or 1 qubit in isolation, you can operate it pretty well, but you might come up with ways to operate it that don't extend to larger numbers. So it's important to do this, but it's also important to look at them at, say, a 9 qubit chip like what Amir's doing, learning how to calibrate it and thinking about, how do I get all the wires into those qubits, right? If you have 1 qubit, you can just bring them in from the sides. If you have 2 or 4, maybe you can still do that. You get to 10 or 20 and you realize that there's not enough room to bring everything in from the sides. So you have to come in from the 3rd dimension. So we focus a lot on these types of practical issues. We think a lot about quantum control and how do we best mitigate errors. We know that quantum error correction is possible, but boy, is it expensive. So anything that you can possibly do to prevent or at least push that off as far as possible, we know we're going to have to do it, but just mitigate those errors as much as possible before we have to do, okay, we got to do error correction for these errors. Some recent work in the group was we asked the question, what's next in the coherence limiting effects in the environment? And we've been chipping away at these as a community for many years. But we looked at cosmic rays and radiation. In fact, the walls of our labs also have radiation. It's at a very low level, don't worry, but the qubits can see it. And so we started studying that. And indeed, that's going to limit us to the millisecond level of coherence if we don't do anything. Of course, we're going to do something, but first you have to know the problem and then you can attack it. And it also leads to an interesting question related to error correction, which is that if you have one of these absorption events of a high energy radiation, of course, it doesn't just affect 1 qubit, you see errors on all the neighboring qubits as well. And so what do you do in that case, right? And how do you modify your error correcting codes to handle such correlated errors? Or if you can't do that, then that says to the experimentalists like us, well, we better come up with a way to make sure that doesn't happen, right? So these are the kinds of directions that we've been looking at in my group. And I think thinking about, maybe the last thing I'll say is that it's too easy, and this is in the hype era, right? It's too easy to say quantum computing will revolutionize machine learning. Quantum computing will revolutionize X, where X could be just about anything that will allow you to make some money and is commercializable. Maybe it will. But what I would say is that we actually have to take a real problem and show me how quantum computing will solve that real problem. right? And I think because it's very hard to solve an abstract problem. You have to solve a real problem, right? Neck it down to something that you can hold in your hand and say, all right, how do I do this? I think that will be very fruitful because it'll point out exactly what we know how to do and what we don't know how to do. And once just like this example of, seeing what you've got and then solving that problem, I think once we understand what we can and cannot do with quantum algorithms, that will motivate us to find a commercializable algorithm or develop new algorithms that solve real problems. I think that's very important.
Thanks for those. Thanks, Will. Those were great insights. Spiros, can I pass the torch to you now?
Sure. I'll since Will is the expert on this, and also he perfectly covered to some depth actually quantum error correction and scaling up, extending quantum devices. I'll answer this from a different point of view, which is that of games. So a big part of my days at this time is trying to develop a new genre of games, quantum games, such as quantum chess, tic-tac-toe, things like this. But in collaboration at this point with Google Quantum AI, we've ported some of these games on the quantum cloud, right? So I see a future where kids of all ages will be playing quantum games and learning without realizing that there is anything educational about them. You're just, messing around. And because there is superposition and entanglement and interference effects that are just part of the gameplay, you'll start developing intuition that goes beyond our intuition. And we've spent like a couple of decades, building it through linear algebra and so on and so forth. So I find this very exciting because it will go hand in hand, I guess, with developments and increasing the fidelity of qubits and quantum gates and error correction. How smart can we be as we develop on these platforms interfacing with these quantum machines in the cloud? How smart can we be to push these games to be as exciting as possible without using quantum resources that are not reliable yet, right? How can you create hybrid classical quantum games where you outsource only quantum states as much as whatever is needed, you sample them, and then you use again classical post-processing or pre-processing to do the rest of the work. And what would that lead to, right? We're going to have Ant-Man 7, I mean, the next Ant-Man is going to be called like Quantum Mania. So I got that in, right? But what is going to happen after that, right? We're going to have them playing quantum games, and which is also part of my my everyday work, is like answering emails or having meetings with fancy people like Keanu Reeves or Brie Larson or whatnot, which is insane because these are my heroes growing up, right? And now they're like, how do I add quantum field theory to my comic book, right? how do I rewrite this part of the script so I'm a quantum cryptographer? I'm like, okay, I have people I want you to talk to. So it's exciting that quantum computing itself is unleashing so many interesting new possibilities in not just quantum computing and engineering, but just quantum itself, right? It's becoming part of the mainstream. I'm part of an executive committee that is working to celebrate the quantum century, 100 years of quantum physics, like in a few years, to try to develop the workforce, right, through this part of the National Quantum Initiative. And it's pretty exciting. I mean, this is exactly why when Kira reached out to me and said, like, hey, you want to be part of this advisory board? I'm like, hell yes. You guys are already doing some amazing work. I mean, nobody else is doing something of such high quality and also so broad, like, from around the world, all of the students, like thousands of students. It's just unimaginable. It's really amazing.
Yeah, I mean, that is truly amazing. The fact that quantum is in the name of one of the Marvel movies, I'm very much looking forward to that. And Scott, finally, I would like to ask you the same question.
Yeah, so I can't say I spend quite as much time as Spiros does hanging out with Keanu Reeves, but but I am excited about things right now. I mean, maybe most obviously, we have finally entered what John Preskill has called the NISQ era, right? The era of noisy intermediate scale quantum computers, not error corrected, but you've got, 50 or 100 programmable qubits. And now, something new is happening, from my perspective as a theorist, which is that the experimentalists, instead of just being off in this, totally orthogonal direction, we're kind of cheering them from the sidelines. They are coming to us, to the theory community, and saying, okay, we've built this thing. Now, what do we do with it? What do we do that is interesting, or that is hard to simulate with a classical computer, right? And we now have the first claimed demonstrations of quantum supremacy based on sampling problems, but that is really just, the very, very beginning, okay? Because now you could ask, well, are we really confident a classical computer can't spoof this? How can we make this harder to spoof? How can we do something where a classical computer can easily verify the answer, where we don't have to use this gigantic exponential time brute force classical computation just to verify what the quantum computer did, right? Can we do something using these noisy 100-qubit devices, which is actually useful to someone, right? That might be as simple as generating cryptographically certified random bits for use in cryptocurrencies, for example. It's something I've been thinking about. It could also be simulations of condensed matter systems, maybe even simulations of quantum gravity, right? So there's a lot to explore where theory and experiment can actually talk to each other, as they never really did before in our field, right? But in addition to that, I'm excited by the breakthroughs that there have been in theoretical computer science over the past decade, about especially about how to verify quantum computations classically. Okay, so there was and quantum interactive proof systems. Some of you might have heard there was this breakthrough protocol by Urmila Mahadev 3 years ago, where she has shown how to take any quantum computation and use cryptography to have it prove its answer to a purely classical skeptic, that it communicates with through a classical channel over the internet, let's say. That solved a problem that I had popularized on my blog for many years. I think it was first raised by Daniel Gottesman. There was just a year or two ago, there was in one of the biggest breakthroughs to come from our field, the MIP star theorem, right, where it was shown that if you have two quantum provers who are separated from each other, so they can't communicate, but they can share an arbitrary amount of entanglement, then they can prove the answer to the halting problem, right? They can prove that a certain Turing machine halts, and they can do that quickly, completely independent of how much time this Turing machine might take until it halts. So this was the first time that quantum computing actually reached beyond complexity theory to affect computability theory. This has had ramifications for pure math. Refuted a huge conjecture from the 1970s in operator algebras. It's had ramifications for the foundations of quantum mechanics. And then this all came out of just thinking about quantum proof protocols, and there's a lot more to do there. I am excited about the fact that the string theorists, or former string theorists, now increasingly speak the language of quantum computing and information. This is largely due to the efforts of Lenny Susskind and his friends, who started something called the It from Qubit collaboration that has sort of rephrased the discussion of, for example, the Stephen Hawking's black hole information paradox and the ADS-CFT correspondence, in the language of qubits and entanglement and quantum circuits and even complexity, to the point where even I have been able to get involved sort of on the fringes of this effort. So at least when they can boil a question down to where I can understand it, then I can try to help the string theorists as a theoretical computer science consultant. Okay, but this is the type of connection that I would say I only dreamed about when I was a student, entering this field 20 years ago, and now it's really happening. So those are some of the things that I'm most excited about right now.
Thanks, Scott. That was a really, I think, great overview of why the field is so exciting right now. And I'm pretty confident it will continue to stay exciting in the years to come. And hopefully our students can continue to make it even more exciting in the future. So I guess with that, we've had a lot of students go through this course over the year, and they've learned quite a bit, but along the way, it hasn't been an easy journey. Learning quantum computing is no easy feat. And I think one of the most fundamental aspects of learning in part is failure. And given that you all are giants in the field, I think it would be great for students to hear about times that you have potentially failed in your research or any kind of endeavor, and sort of how that helped you move along. So I guess I'll pose this to Spiros.
Sure. Man, if I don't have enough time to tell you like how many times I failed, maybe I could tell you that 2 times I succeeded instead. I mean, I just, on a more serious note, when I first had to learn what a tensor product is, and your students probably are now like, okay, the tensor product, the dreaded thing and all that stuff. It took me so long to really figure out what it was, because I want to understand mathematically what is it, and then my mathematical physics PhD advisor would just tell me like, oh yeah, it's this multilinear thing and all that stuff. I'm like, no, give me a little matrix and tell me what is the tensor product between this 2 by 2 and this 2 by 2 and how you compute it. Okay, it was funny because I wanted to understand something, even though I was supposed to be a more abstract mathematical mind, by looking at numbers in front of me and just seeing the pattern of how these things were multiplied, right? And then all of a sudden from there, you go much further, right? Once you have something concrete, and I'm sure your students have also figured this out by now, then they can soar freely up into the skies, okay? Just a few little concrete things and they can bootstrap beyond. But one of the hardest times for me was indeed when I was working on the quantum Hall effect. It was insane. It was, I was at Los Alamos National Lab at the time. It was my first postdoc right after getting my PhD at Davis. And it wasn't just that it was a new place and never been to, New Mexico, and it's a different culture and all that stuff. That wasn't it. I was like, okay, I'm up in the mountains. That's where Oppenheimer and Feynman and others just built the atomic bombs. All right, I'm not a big fan of that, but at least there's a reason why it's so isolated. Okay, they took them up there for a reason, but it felt that I was working against something that it wasn't anymore like a homework problem, an extremely difficult homework problem that maybe one student over the decades of professor teaching it had solved, and they're like, all right, they kept giving the same problem to the next generation of students. Maybe another person will figure it out. This was nobody knew, right, how it was going to be resolved. My advisor at the time, Matt, had a good idea, but again, he had been working on it himself for a few years. And there he's like, would you like to work on this problem? And I didn't know even what the quantum Hall effect was. As a mathematician, I hadn't heard of it before. And it's terrible because now once I got into it, I was like, okay, there's about Nobel Prizes, to its name, and all this amazing work, a whole new field exists based on that. But at the time I was just completely isolated and I had no idea what was going on. And, I said earlier, it's important to slow down and to get comfortable feeling dumb. One of the greatest superpowers of some of the smartest people I know is that they become comfortable at some point in their own ignorance, but also virtual incompetence, right? Or feeling like I just suck at this. I'm anybody else would have figured it out by now and all that stuff, but yet I can't. But to be okay with that, right? Because it's usually an illusion anyways. It's like when you're in a classroom, even in high school, but then especially when you go to college, and the professor says something, and I guarantee everyone is thinking at the same time, I don't know what that means. Okay, like nobody, they're all equally confused, and just one person, right, has the courage to raise their hand and say, Professor, I know this is like a naive, dumb, blah, blah question, but could you explain this thing again? And there's a collective sigh from 400 students, like, yes, thank you. You know, like we're all feeling exactly the same way. And it's important to remember that feeling. It is basically always this way, right? Just like we are not so much more special in our intellect than everyone else, we are also not that much more special in our inability to understand things than other people. Just take time and figure it out in your way. The way I was able to help solve the problem in the end was by starting from nothing, right? Because I couldn't read the vast literature of the quantum Hall effect. So I just went the most basic way, like the dumbest way, like just break it down to simple parts and then build up everything from there. It paid off and I learned a lot. Like it's a great way, I think, to do things.
Thanks, Virus. I think that's very inspiring for all of our students. Some great advice there. I'll ask Will, I guess, now to answer the question as well.
Yeah, sure. So I agree with what Spiro said, and I don't really like the word failure. I mean, it's a word, and we're stuck with it because we don't get to invent new words like this. But for me, it's part of the process, and it's without making mistakes or attacking a problem and running into a dead end, forcing you to think about a problem in another way. I don't think that we really solve and learn, right?
Oh, did Will cut out?
Hear me? Oh, did I come back?
You're back.
Yes.
Oh, okay, sorry.
Okay.
So what I was saying is that I tell my students, and Fran and Amir have heard this, is that when you do things, things get done. It's a tautology, I know, but it actually is pretty meaningful, which says that don't get paralyzed by thinking about something, trying to get the ultimate final answer to get started, because that's really challenging. And in fact, it's one thing that maybe I'll also mention is that in the transition from being a student to a researcher, there's a evolution that happens. And what that is that rather than being a person who reads a book and listens to what the teacher says and then reproduces it on an exam, you become someone as a researcher who's finding new knowledge. There is no book where it's written and it hasn't been done before, and you're going to do it for the first time. And that process, by construction, there are going to be dead ends along the way, right? You're going to try something, it's not going to work. You're going to try something else. You're going to try something else. You're going to get lemons. You're going to make lemonade out of it. All of these things are going to happen. And I don't view that as failure. I view that as the path towards success. So we're stuck with the word failure, but when you feel down and things aren't working and you just can't get it, take a breather. It's okay. And come back with a fresh mind and try again, because I can tell you, I think all of us here, but I'll speak for myself, that happens to me almost every day. So don't let it get you down. Use it as motivation that I know I'm on the right path because I now know something that doesn't work and I'm going to find something that does now.
Thanks, Will. And last, I'll ask Scott.
All right. Well, it's hard to know where to begin in enumerating my failures, right? I mean, the first summer that I spent in quantum computing working with Lav Grover, I completely failed in my project, which was to try to lower bound the quantum query complexity of an AND of ORs tree. And, I was trying to use this method I had learned called the polynomial method, and couldn't make it work. And then indeed that wouldn't be done for another 13 years or so. But then the fall afterward, Andras Sambayanis solved the problem by inventing a completely new method for proving quantum lower bounds. And I got an early copy of Andrus's paper and was completely blown away by it. And the good part was that because of all of the time I had spent on this problem failing, when someone else solved it, I was able to understand the solution, right? I was able to say, I would not have thought of this, but now that someone else has, I can understand it. And then a year later, I ended up working on a problem that Andres had actually invented his method to try to solve, which was this collision problem, where he couldn't get it to work for that. And I spent 4 months on that problem, just failing over and over and over. When I finally got it to work, the file that I sent to my advisor, to Vazirani, was called like collision23.pdf. Hey, that was because of the 22 failed attempts before it, right? But what ultimately worked was the polynomial method that I had tried to use for the other problem and that hadn't worked. So, I found again and again that even when I failed to do something, I've been able to sort of take what I learned, and what I learned was usually useful for something else, right? And the other central thing that I would want to advise everyone about failure is that, one of the least acknowledged secrets of research is the ability to redefine your failures as successes. Okay, or in other words, your arrow misses the target, so now you just draw a little target around wherever the arrow landed, and you write a paper about how that, telling a story about how that could have been a reasonable target all along. Okay, so I spent 6 months around 2009 working on this problem of BQP versus the polynomial hierarchy. I completely failed to solve it, but I decided to write a paper about it anyway. Just saying, here is my program for solving this problem. Here is why the existing techniques aren't working, why we need a new technique. And then, a decade later, Ron Raz and Avishai Tal were actually able to complete that program. Okay, so it ended up being a useful paper in that way. The boson sampling paper, was maybe my most influential paper, but the truth is we failed to prove the central statement that we wanted to prove, which was about simulating boson sampling experiments being even approximately being hard for a classical computer unless the polynomial hierarchy were to collapse. Right? We conjectured that, we failed to prove it, so we could have just decided not to write anything. Instead, we decided we're just going to boldly, take whatever we need to be true and just state it as a new conjecture. And then just say, well, assuming that conjecture, we're going to show that everything we want would follow from it. Okay? So that's what we did. But there are many examples where papers that ended up being tremendously influential, are ones that the authors almost didn't publish because it seemed, at the time, like they just failed to do the thing that they really wanted to do. Okay, so I would say publish your ideas and let posterity sort out which of them are important.
Thank you, Scott. And I would like to conclude the panel by asking each of you, what is the advice that you have for high school students or people in the earlier parts of their education to learn quantum computing and to continue in the field? Oh, and let's start with Will.
Yeah, sure. The field called quantum computing is very, very broad. It's everything from, complexity theory, as we've heard about, to, 3D integration, as I had talked about, and maybe even marketing, as we see in this age of hype. What I would say is most important is not so much that you study these 3 classes, and if you do that, everything's going to work, but rather that you follow your passion, that you find something that you really, really enjoy and follow that and draw a connection between what you like to do and quantum computing. Because I feel that this path will allow you to get up every day excited to do quantum, and you'll have something to offer because it'll be something that's really in your heart. So that would be my advice, is follow your passion of course, study science and study engineering and study the classes that you need to take to get those degrees and do well in them, but do what you enjoy, because there's really a wide range of engineering and science disciplines which will have impact on quantum in the future. There's not just one, it's actually quite broad.
Thanks for that, Will. Spiros, what are your thoughts?
My advice is very simple. Read the magazine called Quanta. Basically, that's that, right? And usually it's Scott talking also about quantum computing there, but it is a fantastic place to go to get inspired about all the exciting things that are happening. It goes beyond, it's almost like I'm just promoting them and getting some commission from, they don't need that. They have so much money, the Simons Institute. But they go beyond the usual stuff that you see even in the press. They can go deep, but still be very inspiring and see the broad picture connections to the future between quantum computing, as Scott also mentioned, like, even how physical reality works at its fundamental levels, things that are very exciting, right? And if you fall in love with this because you're like, okay, maybe we can use them to time travel by creating traversable wormholes, and quantum computers can just compute and unscramble the information at the boundary and all this stuff, it's going to be, you are so lucky, like all of you listening right now, you are so lucky to be alive right now. And for people like Fran and Amir and Rachel and Kira to exist, to give you this opportunity to fall in love with quantum. It's not just quantum computing. It's just, it's the language of the universe. And in fact, I think you can go even beyond, since I've been studying the mathematical foundations, and there is amazing stuff going on there about even theories of knowledge, right? And empathy and, connections from different points of view. It's just amazing. Just go for it. As Will said, follow your passion, have educated guesses about what huge science fiction problem you want to solve seriously, right? And we are closer than ever before to just being able to do this stuff, right? It's almost like science fiction writers are going to have trouble to keep up with us and with you, right? As you're coming up with amazing new ideas, technologies, conceptual frameworks. And the funny thing is that, it's part of all of this is connected with something that is kind of almost purely engineering, right? Building a quantum computer, but it's almost like you're trying to rebuild the universe, a mini version, like Scott's original dream, okay, of trying to simulate his own mini universe. And that's what he's been working to create anyways, right? Which is a quantum simulation, right? Maybe we're not a classical simulation of some kid playing like, PlayStation 12 or something, but this is probably a quantum simulation, and, learning how to do that and appreciate what it looks like from the outside in. It's a very powerful thing. It and also allows you to see the universe outwards and be like, this is pretty amazing that it all works. Like, this is insane because it is a quantum universe. So how does it all work?
Thanks, Spiros. And last but not least, Scott.
Yeah, so I would agree with follow your passion, even to the extent that you don't have to do quantum computing, right? There is value in having people doing machine learning, doing cryptography, doing bioinformatics, doing climate modeling, doing anything else, who are aware of, what is the state of quantum computing, right? And who are, sort of ready, when it becomes available to, sort out reality from hype and so on, right? And I hope that many of you, become those people, right? And quantum computing started in the first place, by a few oddballs, really, Deutsch and Feynman and so forth, following the logic, of certain premises, even, way out on a limb to a place that seemed bizarre and, science fiction-y to most of the people around them, right? So, it's good to be inspired by their example, right? And be sort of, I would say, radical and conservative at the same time, right? Just taking certain principles that everyone accepts, like in their case, principles of computation and of quantum mechanics, and just seeing where they lead when they're put together. The other thing I would say is, if you are going into quantum computing, I have almost never regretted the time that I have spent learning new math. Almost everything is usable, in some way. I mean, certainly, linear algebra and probability, and just knowing your way around vector spaces, right? Is like, it just never ceases to be useful. Any new trick that I learn will probably find its way into a paper, right? So, I mean, I get inquiries all the time from students who are wondering what courses to take. They might be at a university that doesn't have a quantum computing course, but I say, like, if you just have you exhausted what's available to you in learning, just linear algebra, learning group theory, learning classical theory of algorithms, right? Because all of that stuff, if you want to work on quantum computing from the at least from the computer science side, the physics side is another story, but you're going to be drawing on all of that.
Thanks so much, Scott, and all of our panelists. I couldn't think of a better way to end this panel. And I guess I will pass it back to Rachel for the next part of the final class.
All right. Well, best wishes to all of you. Thanks for having me.
Yeah, thanks for having me too. Take care.
Thank you all so much.
And congratulations, everyone.
All righty.
Yes, congratulations.
Can you guys see this?
Yeah, it looks good.
Cool. So we have a full agenda left. Just an incredible conversation to end the course on. Thank you so much to Will, Spiros, and Scott for spending time with us, and for Fran and Amir facilitating such a great conversation. We will take a super quick break because we're going to try to keep this to 2 hours if at all possible. However, before we do that, we did not plan it to be this way, but today is Amir's birthday. So we will open up the chat and allow you to share your birthday wishes and gratitude to Amir for all of his work helping to co-teach this class, and best wishes for the year ahead. And with that, we'll do just really 3 minutes for a break. And after that, we'll have a speaker from IBM, and we'll hear our surprise from our TAs and hear from Phil and Akshay. So with that, we'll take a quick break and see you all back at 24 after.
Wow, Amir, 1900, happy birthdays. Thanks, Fran. Thanks, Amir.
Thanks so much, Will. Have a
Thanks
good
for
rest
coming,
of the
Will.
weekend.
And then did Scott already jump off? Yeah, looks like he did.
Did.
All right, I'm gonna have to jump off now too. So we'll see you guys.
Great to see you, Will.
Thank you for having us again.
Thank you, Spiros.
Yeah.
Thanks, Spiros.
And happy birthday, Amir.
Thank you.
All right, if folks want to come back, sorry for the quick break, but we still have a lot to get through. So we now have the great opportunity to hear from Carmen from the IBM Quantum Community Team. Carmen's been a surprise because Carmen's sister, who's 15 years old, is actually in this course. And so hi to Carmen's sister. Carmen works on the community team in Europe. So she's based in Zurich, Switzerland, and we'll be sharing opportunities to stay involved with IBM and Qiskit, but also just her experiences working in the quantum field and reflections about being at IBM Quantum. And with that, Carmen, we will turn it over to you.
Thanks a lot, Rachel, and thank you also for inviting me to be here today. I'm super excited, as Rachel explained, because my little sister is one of the students, and this was a secret. But I don't want to congratulate just my sister. I think it's amazing that all of you have been through working all these months through this course. And I think that right now we should be talking about what is next. So that's what I'm gonna go ahead and explain now. Zoom is telling me that I cannot share my screen. I think I need some kind of permission. Maybe you need to make me host or something.
You should be good now, Carmen, go for it.
Yeah, thank you. Okay. So can you see my presentation now?
Yep, we can see.
Perfect. Okay, so after all these months learning from such amazing teachers, I just want to kind of give you the idea of what can you do now on your own, now that you have such a good basis to get into the rest of the things that you haven't learned so far. But the first thing is to congratulate all of you. I think it's amazing, all the work that you've done. And these were a lot of months. I don't think that there was such a course before this one. So you are like the pioneers in this kind of education. So congratulations to everyone for being here today. And let me also introduce myself because I think I might be an example, a weird example of how to get into quantum computing. I come from Spain, and I studied my bachelor's in mathematics in a university in my country. And after when I was studying, I didn't even know that quantum computing existed. In the last year, I discovered artificial intelligence, and since it was something that appealed to me a lot and it looked super cool, I decided that I wanted to get out there, start working, and see what companies, science companies and tech companies were actually doing with AI. And that's how I joined IBM for the first time as an intern, but in the AI hardware department. Also, during these years, I was always very active in the tech communities, because as you know, the same way that the Qiskit community has such a lot of people contributing because it's an open source project, there are also other technical communities, like maybe around programming languages such as Python or other kinds of technologies. And I was always very active in the local communities in my city, which was Madrid by the time. So during these years, I was so lucky and I got the chance to meet a lot of people who inspired me. I went for the first time to a quantum computing lecture in a university. I found out about it via IBM, via a mailing list, a random mailing list that maybe I just read by chance, and I just fell in love with it. And during these years, I got the chance also to travel a lot. So that's why I'm saying here that I went to Boston, to New York, Greece. And in every single place, I met someone who inspired me. That's why I think it's, and I highlighted this word, it's so important to have role models and mentors throughout your way. These are the people that actually inspire you and give you the ideas of what you want to do next. So it's fine if you don't know yet what to do, but in doing this kind of things, like participating in this course, I'm sure that you have met a lot of role models. And also another thing that I think was important throughout my way was to volunteer. So every time that I saw something that interested me, I volunteered for it, even if maybe that wasn't my team. And so that's how I started working with the IBM Quantum Community team, just as a volunteer. It was something that I did in my spare time, and we started a community in Madrid. We organized a hackathon. Actually, the first QxQ hackathon in Europe happened in Madrid because of the people that were super excited about QxQ, and we were lucky enough that the IBM Quantum community team agreed to organize it with us, and they actually came. And also, thanks to that, I met the researchers in the quantum team, and that's how I decided that I didn't want to be a data scientist anymore, but that quantum had won my heart, let's say. And so I found the opportunity to move to Switzerland. That happened just a couple of months ago. And now I'm working as an intern in the community team, but I plan on doing my PhD in the quantum applications team. And also here in my current role, if it was just the definition of my current role, I will be doing these community-related activities, but because I volunteer for everything, I also get to collaborate with the research group. So from time to time, I work in small projects with them, and this is also really cool. So my message here is I come from a completely different thing, which is AI. I started working, and then because of the role models and inspiration that I got throughout these years, and for volunteer and always daring to ask, I got to where I am today, which I heard that in the panel, someone mentioned that they were doing their dream job. I think this is my dream job too. And I think this is an example that you can do it too. So after that, you heard so many times throughout this course that quantum computing is such a multidisciplinary field, and that there is a space for everyone. So I wanted to give you an example of some people in my team and how do they look like, what do they do, so that you see how this diversity translates to an actual quantum team. And to let you know that this is true, that wherever you are in the world or wherever you come from, there's a place for you. You just gotta find where you can contribute to. Whether you are more interested in the developing part, there is a huge engineering team that develops QxQ, the tools you have been using, like the IBM Quantum Experience. Also, there are mathematicians, there are chemists, there are physicists. So there is room for everyone, and also for every nationality. Actually, in my team, I think that we are only 2 Spanish people, and the rest of the people are each one from a very different country. So that's super cool too. So to give you some examples, for instance, we have here Pauline, who is French. She's a chemist, and she's doing her PhD in quantum applications. Then there's James. You may know him because he's like a superstar in quantum games, and he works also in error corrections, but he really loves coming up with video games, quantum video games. Then we have Almudena. She's a mathematician, and she's doing her PhD as well in quantum algorithms, more related to optimization or quantum finance and this kind of quantum machine learning as well. Then there's Caroline. She's from the Netherlands, and she's doing her PhD in Germany. We have Amira, that you probably already know because she's also a superstar in quantum. And Abe, I think he doesn't need an introduction. He was actually the one who asked me to be here today, so that's super cool. He's all in all the QxQ videos, so you probably already know him. He finished his PhD last year, actually, in Princeton. Then there's Krista, she's from Austria. She's a physicist, and she's also doing her PhD in IBM here in Zurich. Then there's Elisa, she's doing her PhD in theoretical physics in quantum information theory in ETH, Zurich, and she's from Germany too. And then the last example that I bring today is Fabio. He's actually the team leader for Europe. He's Italian and he's an experimental physicist. And right now he's focused in these community events. So I think that this is a reminder of how, let's say, how very different backgrounds have a place into the quantum computing field. And if these people could do it, I think you can do it too. And now, because of these kind of initiatives like Qubit by Qubit that lets very different people in the world, all around the world, learn about this field, I think we are, thanks to these kind of initiatives, the field will get more and more diverse over time, because thanks to the education of many different people, we will have more different, well, we will detect talent in people all over the world. So that's super nice. What kind of activities do we do in the community team? And also I wanted to prepare you like a checklist of all the things that you have available if you want to keep learning after completing this super cool course, 8-month course that you just did. And there is a lot of things that you can do actually. So basically the highlight would be to keep engaging with the IBM Quantum and QxQ community, because there are many things that we keep organizing. The first thing that we have in the list would be to join the mentorship program. This is a program where you get to work in a project for a couple of months. It's a short project. And what is super nice is that you get someone from the QxQ team to be your mentor. So any questions that you have throughout the project, you can ask that person and you get to work together with that person. And there are super cool projects that have been developed. So you can also check QxQ Medium to check what some of the examples of these projects are. Another idea will be to apply to become a QxQ advocate. The QxQ advocates are defined as the more enthusiastic members of the QxQ community. And basically, there is like a small exam that you have to do. And also you have to give proof of, I think it's 3 contributions that can be code or other things. You can find more information in the link that I provided here, that I think the Code School team is gonna share with you afterwards. And basically it's super cool because you also get to be part of this QxQ advocates community. We have from time to time meetups. We have also calls to when someone is doing something cool in some part of the world, they organize a call and they share it with the rest of us. And there have even been some working groups that have met there through the QxQ Advocate program. We have a channel in Slack. And yeah, basically it's people that really like QxQ and maybe they organize events, or they also collaborate in other events. Maybe when there's a hackathon, they also volunteer to be coaches, to be judges, etc. So I really think it's super cool to be part of this community. So I encourage you to apply if you like it. You have all the information in the link and the current list of members that you will see. It's all over the world. The third thing in our list would be to become a certified developer. Probably you will need to study a little bit further, but don't worry, because there are some study guidelines in the information in this webpage that I shared with you. And basically, this is a certification that we launched this year, so that people that work with QxQ and they are becoming experts, they can actually certify it. It can also help you maybe find a job or an internship in well, not concretely this certification, but I mean, if you know QxQ, I have even seen some job opportunities that look for a QxQ engineer. And yeah, so it's super cool to see that right now there are some quantum startups that are looking for this kind of skills. And well, of course, also in other companies and other other frameworks for quantum computing, but QxQ, it's one of them too. Then the fourth thing, the fifth thing that the fourth one, the fourth ingredient in our list will be contributing to open source projects in QxQ. And here you can focus in whatever you like. So there are some, if you go to the GitHub project, you can check the issues, and they are labeled by different categories. One of them is good first issues. So if it's the first time you contribute to a project, that will be a good way to start. Then maybe you don't know a lot about how to code, but you know a lot about algorithms, or you would like to do a tutorial about some paper that you've seen and you want to implement it with QxQ. Then maybe you can contribute with a tutorial. So everything is open. This is there are a lot of things where you could contribute. And of course, we're always happy to see how the community is growing, and the contributions and the ideas they come up with. For example, many ideas from hackathons have become actually projects that are still being developed in QxQ. Another thing will be, we invite you to participate in the community events. So we organize meetups. Sometimes they are global, sometimes they are more local. Another example would be the educational things that we organize, such as the QxQ Summer School. There is one happening this year. I think it's next month, and it will be focused in quantum machine learning. So now that you have all the basis for the quantum computing part, if you are interested in quantum machine learning, I think you will really take advantage of it now that you have all these bases. Also, we organize hackathons. Of course, they were super nice when they were face-to-face, and we will come back someday. But they are also, we are also organizing some of them virtually. And it's also cool because it gives you the ability to have more participants and meet people that are maybe in a very remote location that you will never know otherwise. Another kind of activity that we organize are the IBM Quantum Challenges. There is one that will happen, I think, in 2 weeks. And that's a really nice way to learn, because if you are working in a challenge, you kind of forget that you are learning. You're just trying to solve that exercise, and you will learn anything you need in order to solve it. So I really recommend it as a very nice way to learn. And the last point that I added to the list is to take advantage of all the educational materials that there are online. The one that I like the most is the QxQ textbook. I leave you here the link. Probably if you will have tried to read it before starting this qubit by qubit course, it could have been a little bit overwhelming, but right now I think that all of you are ready to deep dive and learn more concepts while learning how to implement it with QxQ, which is also very useful. And another part that maybe people forget about is that actually you can also learn with the documentation. And the QxQ is making a lot of effort in having a strong documentation with examples and also tutorials. But even the documentation itself, it's a super nice way to learn. For example, I would recommend you also to try to implement the results of a paper. That's a way, that's an exercise that will make you go look up in the documentation what you need to code in order to implement it. And again, you will forget that you are learning. You will just be focusing in trying to mimic the paper results, and on the go, you will learn a lot. And finally, of course, you probably already know it, but I didn't want to leave without mentioning that you have the QxQ YouTube channel. There are a lot of contents there. Also, the QxQ Summer School from last year. And we organize a lot of things, so I would recommend you to stay tuned. And with that, I want to thank you on behalf of the QxQ and IBM Quantum Community team to thank you for being part of our community. It's so nice to have such enthusiastic and talented people from all over the world. And I want to tell you to let's keep learning together. And with that, I think we have some time for questions.
Thank you so much, Carmen. Just reminding us all that this course was just the start of your journey. So many students are already asking what we can do next. So plenty of opportunities with IBM and QxQ to keep building your skills and learning more. We are unfortunately just watching the time. We're gonna probably skip questions, but hopefully folks will have the chance to interact with you through community events and meetups around the world. And thank you so much for joining us.
Course. Yeah, thanks a lot. And if anyone has questions, then you can reach out to me via LinkedIn or Twitter or in any of the events that we organize. Thank you.
Perfect. Thanks, Carmen. Alrighty, just a few things left, students. We will have the opportunity to hear from Akshay and Phil from our teaching assistant team, folks who you know really well. But before we do a quick panel with the two of them, like I've been saying a few times, our TAs prepared a surprise for you. So I'm going to share my screen and they've prepared a few words to say goodbye and good luck.
Hi, my name is Aziza.
Hey everyone, this is Akshay.
Hi everyone, my name is Alina.
Hi there, my name is Corbin.
Hi, I'm Leah.
Hey guys, I'm Aman.
Hi, my name is Sarah Mashinsky.
My name's Amin.
Hi, I'm Phil.
Hey, I'm Rahul. I am mostly a postdoctoral researcher at University of Maryland, but sometimes my wave function tunnels into being a qubit by qubit teaching assistant for you guys.
I'm one of your qubit by qubit teaching assistants. I'm a qubit by qubit teaching assistant.
And I'm a qubit by qubit TA.
And I love being a qubit by qubit teaching assistant.
And I'm a qubit by qubit teaching assistant.
I'm a qubit by qubit teaching assistant.
I'm a qubit by qubit TA.
I am a qubit by qubit teaching assistant.
It was an amazing experience to talk to you about the very cool concepts in maths, physics, computer science, and quantum computing. I know, that's a lot for someone who's just getting started in this field, and I hope you remember how far you've come.
I hope this course provided you the joy and awe of learning something new. And I hope this awe and joy is your lifelong companion, and it acts as a lighthouse to shine your path no matter whatever path you take. And if you enjoy your path, then your journey is by definition successful, no matter where destiny takes you.
As you continue with your studies and exploring quantum computing, I hope that you'll remember what it's like to learn really cool technical concepts. Quantum computing, for better or for worse, is widely known as a very difficult subject. It's very complicated,
And there is some merit to that because, as you've learned, you need to pull in knowledge from math, from CS, from physics, many others, in order to get a comprehensive understanding of this single subject that we call quantum computing. But coming out of this course, you've done it. And yes, it is challenging at times. Yes, you have to review materials sometimes. Yes, there's going to be things you don't understand. But I hope you'll agree with me that the satisfaction and feeling of accomplishment you get at the end is well worth all of that effort.
This stuff is hard. If you're going to try to learn anything like quantum computing, it's going to involve a lot of failure and a lot of frustration because it's definitely hard. But what I want you guys to learn or to remember is that learning is iterative, and you have to keep going back to concepts over and over again until you really master them. And it requires a lot of patience.
If you take one thing from this course, it's to not be afraid of things that you don't know and to keep going even when it's tough, because you have a community of people who support you and care about you and want you to succeed.
I think the best way to learn is just by doing it. And I really encourage students to try and make their own projects. Think about how you can build something new. It doesn't have to be the next big app, but it could just be a fun little side project, maybe a short one-day build. And I think those are the ways in which you can really learn these skills and learn how to put them to use.
Each one of you, yes, you, are precious human beings. And as future leaders, I want all of you to be strong. So please exercise, eat well, and sleep well. Take care of your mental health. Seek help when needed. Talk to friends and family. It's trite, but it's important to remember because in highs and lows of research, sometimes we might forget these simple things.
As we start to think about what we're going to do after this course finishes, I hope that you'll all remember we need educators, scientists, engineers, business leaders, and even policymakers to push the field of quantum computing forward. I hope that regardless of where you are 10 years from now, some of you will end up doing just that.
I also hope that you'll stay in touch with the friends you made along the way, whether that be like Discord or in-person events.
I hope you all learned from me, but I also want to emphasize just how much I learned from you and how your questions pushed me to examine my understanding of these concepts and how I talk about them with people both in and outside of the field.
You're going to be a future leader in quantum computing. And as you continue to work on the technology, I think it's also important to think about access to that technology and to make sure that everyone who wants access to future quantum technologies is able to get it.
Something that still amazes me is the scale of this course. How a global community of learners came together to follow the same course across so many time zones and hugely diverse conditions, especially given the current pandemic. Above all, I hope you guys had a lot of fun learning about quantum computing, and I wish you the best of luck for your future.
Thank you all so much for being a part of this course. I'm so proud of all of my students and all the students in general. It's been an absolute pleasure learning with you and answering your questions and having our weekly Saturday ritual for those who are in my lab. So I'll miss you all.
So even though this is a farewell, it's also cheers to your new beginnings.
I'm looking forward to seeing you around, doing physics at a conference, or as a quantum user, doing anything from cryptography to banking to pharmaceutical design. Until we meet again, good luck.
The most amazing thing about this course was the sheer number and diversity of the students. And I hope as future leaders in the world of quantum, you pay this back multifolds by actively ensuring that no one is left behind. And you can start today by talking to your friends, your family, your parents, your grandparents, anyone who would listen, anyone who would not listen. Oh, wait, I think I'm getting decoherent. But the torch is with you now, and spread the word of quantum.
All right. Like the slide said, students in this class turned this course into a community. We are so grateful for all of you. For some final thoughts, I want to call up Akshay and Phil, and then we'll hear from Kira to send us out with concluding remarks. Hey guys, do you want to introduce yourselves just real quick for folks who haven't had the chance to meet you yet?
Yeah, I'm Akshay. I've been lurking in the background for most of the lectures. I am one of the course TAs, and some of you have been in my labs. Yeah, and I'm also currently I'm also currently a postdoc at MIT.
Hi, I'm Phil. I'm an undergraduate at Harvard. I'm a TA, so hopefully some of you've seen me in some of the labs. And yeah, I'm a computer scientist, but I also run a quantum computing club here just for fun. So yeah, we're hoping to just have a little chat at the end and go over some of the things that were on our mind, some of the things we've heard from students too. So I'll pass it back to Akshay to get us started.
Yeah, so one of the things that we've heard very frequently from students is about just how challenging all of this material really is and how hard it is to learn. So I'm wondering, Phil, what your thoughts are about just the challenge of learning quantum computing.
Oh yeah, it's hard. Let's get that out of the way first. It's really hard. It's hard because of all the topics you can cover. It's so inherently multidisciplinary. We had to cover introduction to computer science, introduction to linear algebra, introduction to quantum mechanics in the first semester of this year-long course. We didn't even touch quantum algorithms yet, and we had to do all of this preparation just until we could explain the most basics. And I think that's why it's so hard. You need to be a master of all trades in order to just get your first step in the door. So yeah, it's a really hard course, but I hope that doesn't deter people, because part of the fun thing is by learning and taking all these in together, you're able to really put it together into something greater than all of its parts. By using linear algebra and quantum mechanics to solve a problem, you're tapping into the previous knowledge of hundreds of researchers. You're standing on the shoulders of people that work their entire careers to come up with this stuff. And we're feeding it to you right before a lot of you have even stepped into university, which is mind-blowing. It's so early to get in on this. And it's so much fun because you can use it. Quantum mechanics is abstract, but here we are applying it to problems. We're writing code that uses it. And I hope you're all inspired by that and excited by that aspect.
Yeah, and to elaborate on that, I think also some of these skills that you've learned of linear algebra, of probability, just being able to code and do these things, on a computer, those are going to be really useful in a lot of different STEM fields, not just quantum computing. So I would also say that the skills that you've learned in this course are going to be really, really broadly useful in a lot of different STEM disciplines.
So going on from that, Akshay, what do you think with this knowledge that students can start to do? How far are they away from what the cutting edge of research is? Where are they in their journey along knowledge?
Yeah, it's a really good question. So I think that this is an analogy that Phil gave to me. This is kind of like, suppose you want to climb Mount Everest, right? Now, before doing this course, you're kind of like sitting at home, you have that dream, but you haven't really started. And I would say that now you're at base camp, right? Now you know how tall the mountain is, you know what the challenge is, and you have the tools now to really start climbing, to really start exploring, and to like reach the peak. And Phil, you had found an example of a very recent paper which students can. It's an example of the kind of work that students can now really look at, right?
Yeah. So I was just flipping through arXiv, and today I came across a paper on quantum embedding kernels for NIST computers. Sounds like a ridiculous title, but this came out 2 days ago, and this is a preprint. This is right at the bleeding edge. And just going through the paper, a lot of it's on bits of machine learning, a lot of it's on maths and kernels, but the bit that covers quantum, it describes the entire circuit in about a paragraph. And everyone here in this course, if you were able to do some of the homeworks, you could easily implement this exact circuit. You could try it out for yourself. And it's kind of surprising to think that, yes, we're only at base camp, but base camp is 5,000 meters up. You've gathered a lot of knowledge. Sure, you're not at the peak yet, but you can see the peak. It's only the next, couple thousand meters away, but you're more than halfway there. And I think that's important to realize that these papers are not as out of your reach as you maybe previously thought. This paper is really cool. It promises some interesting dynamics into the field, how this will directly affect machine learning, directly have applications. But honestly, with just what we've covered so far, this should be readable now. I really think that with some time and effort, you can go through it and piece together, I think I know what that means. Okay, they're using a sigma X. Wait, we've covered that. We did a whole week on that. I know what a sigma X gate looks like. I know what gates are. I know what initials. You can actually interpret it and learn from it. And I think one of the main points we wanted to get across was the concept of bootstrapping. And that means you give enough knowledge to get yourself started, but after a while, you can try and iterate yourself. You can try and learn more information, use the knowledge you already have to keep pushing farther and farther. And I really hope this course will not only bootstrap yourself for quantum computing, but bootstrap yourself in a whole range of courses. Maybe now you can do some reading on linear algebra. You can tackle machine learning because you know how some of these underlying pieces fit together. So use this knowledge to your advantage and treat it like a tool.
And I would also add that you now know the width of this field. You're now familiar with all of the different aspects of quantum computing, and you can start exploring if you're more interested in the theoretical aspects of it, if you're more interested in the hardware aspects of it. And I would also add that you are one of the few thousands of people around the world now who have this kind of introductory material. Phil and I were talking a few days ago about the size of the quantum community around the world, and it's really not that big, right? It's a fast emerging and growing field, but right now it's not a very big community, and you guys are now all part of it.
Yeah, it's a cool aspect to think that the field is not that big, and we talk a lot about building a quantum workforce and becoming leaders in this field, but that really is the case. The field is small. We had some of the coolest people in the field speak earlier, and they could probably name every other major researcher. And it's incredible to think just how small it is, but also just how big the applications could be. So be proud of yourself. You're part of a really cool club right now, and you should keep trying to maintain that club, because hopefully this club will do some incredible things in the future.
Yeah, I'm very excited to know where students who started off in this course, where they'll be in the next 10 years, the next 15 years, and so on. Yeah. So Phil, I'm also curious to know if you want to talk a little bit more about what it's like to do research in the field. What does that look like? How do you figure out, here's a good problem to work on, here's what I'm going to do about it?
Picking research and picking topics, that's an interesting aspect. I'm doing that right now. I'm trying to figure out exactly what my thesis is going to be on. And it's fun because the best projects are not the ones which are outlined in papers. It's just the times you think, I wonder what happens if I just try this. And you spend an afternoon and maybe you try a couple things out and you produce a graph or you compute something and the answer comes back and you're like, that's just wrong. But that's how the cool problems develop. I just spent a week working on something. I got my final project graph out. The graph was completely random. I was completely and utterly wrong. And in some ways it's disappointing. Yeah, that means I got it incorrect. I made a mistake somewhere along the way. But also it's really exciting because that means, no, there's more to this question than I thought. I think the worst thing is you find a question, you answer it immediately, and you're like, okay, that's it. But the best projects, the most fun aspect is you try to answer it and you don't get the right answer, and you think, wow, well then there must be something else at play. And you start playing like a game of 20 questions, and you say, well, I don't know if you played 20 questions, you ask like, are they alive or are they dead? And you're trying to figure out what person it is. And it's like you're doing that with a problem. You're trying to figure out, is this still, what happens if I tweak this aspect? And then you get crazy results. You're like, no, that's not right, but let's go down a different path. And that develops into a really fun and exciting project. And the best ones really do start with, I wonder what happens if I try this. So this is really us saying, imploring you to just try it, just see what happens. You know, you tried building a circuit. Can I try and make this, you know, can I try and render a photo, but somehow use a quantum computer to do that? And you start diving into it, and maybe you're like, well, I know there's randomness in this, and like there's Monte Carlo and this and that, and what happens if I just throw this in and throw this in and hodgepodge it all together? But you can come across some really cool insights. So I'm rambling on, but picking interesting topics and projects to work on is a lot less complicated than I think people make it out to be. It's really just a matter of, let's give it a go. Let's see what happens.
Yeah. All right. So thanks a lot, Phil, and hopefully this discussion was helpful to you guys as you go on and try to continue learning quantum beyond our course. And I now want to turn it over to Kira for some closing words.
Thank you so much, Akshay and Phil. I'll just take a few minutes because I know we're already over time. For those of you who do not know me, my name's Kira Peltz. I'm the executive director of Qubit by Qubit and the founder of the coding school. First off, I just want to say congratulations to all of you. This has been an incredibly difficult year, and I'm honored to have shared part of it with you. You truly are at the forefront of this emerging technology, quantum computing, and I'm so proud of all of you have done, and I cannot wait to see what you do in the future. I also want to take the time to thank our incredible team. As they say, it takes a global village to create a quantum researcher, and we are no exception. There's so many people, those who have taught you throughout the last 8 months and those behind the scenes who have put in so much love and time and effort to make this possible. So I want to thank our advisors, our board, our instructors, Fran and Amir, our TAs led by Akshay, our homework led by Brian and Phil, our admin team. This would not have been possible. This was led by Rachel. Would not have been possible without all of the time and effort that she has put in leading this course, and so many others who have played a pivotal role. Also, we could not have done this without IBM Quantum. So thank you so much for believing in us and our students, and really in your dedication to ensuring that there's equity and inclusion in quantum education for all. You know, my goal at Qubit by Qubit is really to ensure that every person has access to accessible and supportive quantum computing education. I believe it's important not just to teach students skills that are important for the present day, but that we must be teaching the skills necessary for the future. These aren't skills that I think are just important for employability, although it's an added bonus, but that we have to create a more equitable and inclusive future where we are all empowered to thrive. And that's why I'm so passionate about quantum computing. Furthermore, this course and our program at large, it's not just about creating the next generation of quantum computing experts and leaders. For me, the goal is really for all of you to take the skills that you've learned in this course and apply them to the sectors that you're passionate about. So I see that we're not just cultivating leaders in the field of quantum computing, although I truly believe we do have some of the most brilliant minds in this course who will go and make incredible, innovative discoveries in this field, but we're also cultivating the next generation of policymakers, of healthcare professionals, of climate change activists who will take the skills that they've learned in this course and apply it to their sectors and subsequently change the world. So I'm so excited for what the future holds for all of you. We will continue to aim to offer innovative programming. And with that, we ask that you help support our ambitious endeavor because we can't do this alone. So please tell your friends and family and classmates about our programs in the future and encourage them to apply, especially encourage those to apply that wouldn't otherwise do it. We have to support each other. Quantum computing, as it was, I'm sure for many of you, is intimidating. And we have to have other people saying that we can do this and push us along. Please tell, if you're in high school, please tell your schools about us and about our course, and encourage your schools to partner with us so we can be offering this for school credit at schools around the world. We may also ask in the future to feature some of you on our blogs or in videos, or for other testimonials. So if we send out an email to you, please respond. And as I like to say, we are now forever entangled. Please don't be a stranger. Keep us updated about your journey and what you end up doing. We want to be here to support you, and to hear about all the incredible work you participate in going forward. So thank you all so much for one of the highlights of my life, being a part of this course and this journey with all of you. And I hope you have a great rest of your day. Thanks, everyone.
Thank you to Kira. And that's a wrap, folks. We will open the chat to say goodbye one last time, but otherwise, congratulations. Thank you for making this experience so special for all of us, and an official welcome to the quantum community. I have some more celebration tunes. All right. I feel like this could go on forever, but we should probably wrap it up, Gabby. Bye, guys.